So far what we have been doing in this class is we have looked at independent voltage sources, current sources, resistors, right? Then op amps. Okay. Now there are two elements that we have not paid a lot of attention to. Those are inductors and capacitors. Okay. So now the reason we didn't consider them is because the minute you include inductors and or capacitors, what you will find is the equations that you have been solving so far, right, are no longer simple algebraic equations, but you will get a system of differential equations. They are obviously one order of magnitude tougher than the traditional algebraic equations. I think you have already learned how to solve some of those differential equations, and we will try to solve them in today's class and in the next few classes. Okay, so we deal with the simpler stuff first and then move on to the more complex ones. So in today's class we will start off with the most basic circuits. We will start off with simple circuits with resistors and capacitors. So today's class is going to be all about RC circuits. Let us start with one of the simplest RC circuits. Okay. This resistance is some resistance R, the capacitance is some capacitance C. Okay. Now I am going to say this is the input here across terminals 1 and 2. The input is applied. I will call that some Vs of t. Okay. Now the minute this is, you know that the capacitor has memory. Remember we pointed out that the capacitor and inductor are examples of elements with memory. In other words, the voltages or the currents not only depend on the present voltages and currents in the circuit, but also the past voltages and currents. Okay. So because of this, you will have to consider the input and or the output as some kind of time varying function, not just a simple just Vs, but Vs of t. And let us say I take the output here. I am going to look at the output or the desired voltage is actually or the voltage of interest is actually the voltage across the capacitor. I will call that Vc of t. Okay. And the voltage across the resistor, I will call that as Vr of t. Now this is the most generalized representation, but let us start off with a, actually if you had to solve this generalized representation, how would you do this? How would you start off analyzing the circuit? KVL, then KCL, and what? Element relationships. It's exactly the same thing, right? What you end up with is not an algebraic equation but a differential equation. But the way of solving these circuits is exactly the same. Remember, KVL, KCL are sacrosanct. They are never violated except in extreme cases. We are not considering those cases here. Okay. As far as we are concerned in this course, KVL, KCL are valid all the time. Okay. And we are going to use these two in conjunction with the elemental relationships to solve the system of equations. Okay. So if you write down KVL, KCL and the element relationships, you should be able to solve this system of equations. How would you propose to solve this? There is just a single loop. Okay. So KVL will tell you Vs of t is Vr of t plus Vc of t. That is what KVL will give you. What does KCL give you? How will you write KCL? Where will you write KCL? You can write KCL at this node. Okay. If there is a current, if this is IR of t and this is IC of t, okay, KCL will tell you IR of t is equal to IC of t. Okay, there is no other path for the current to flow. Okay, so This is KVL. This is KCL. What else do you use? The other two things to use are the elemental relationships, and the elemental relationships are for the resistor IR of T is VR of T by R. So that's number one. Okay. IC of T is, what is IC of T? You there in the blue t-shirt. Yeah, that's you. What's your name? Huh? Pradyumna. Pradyumna, tell me what is IC of T? Yes, but we are not writing down KCL. What are we writing down on the right side? What is it? dQc of T by dt. Can you put it in terms of quantities that we have here? C dVc of T by dt. Sit down. Okay. So these are the four relationships. What are the unknowns here? IR of T, IC of T, VR of T, VC of T. Okay. If you had to put all of these together into a single equation to be solved, okay. Let us say in this particular case we are interested in VC of T. Okay. You can write down an expression for VC of T. So I'll write it down in this form. Because I've implicitly put everything together. I've used IR of T equal to IC of T. Okay. I've used IR of T is VR of T by R. I've also used the KVL expression. So if you want to solve this, if you want to solve for VC, this is the form in which you want to write down the equation. Basically, this is what you would do when you want to solve an algebraic equation. All the, or for example, all the variables on one hand, on one side, the function that is the independent function on the right side. This is similar to what we did for mesh analysis, node analysis, and so on, right? So the independent stuff on the right side. So Vs of T is what is being applied from outside. Okay. What we want to find out is Vc of T. Now, so this is of course a first order linear differential equation. I'm sure all of you have you encountered first order linear differential equations already? You have. Okay. So what we'll do in this course is not to deal, we will not be dealing with these kinds of linear differential equations in a lot of depth. Okay. In the maths course, in the mathematics course, you would have learned LDEs with a lot of rigor and a lot of detail. What we are going to do here is to try to come up with specific, we are going to use it as a tool. What you have learned already, we are going to use it as a tool to solve these kinds of systems. So let us try to simplify this. We want to solve the simplest form of this. The simplest form of this is Vs equal to 0. Right? So let us set Vs equal to 0. See what it gives us. So this is of course a first order linear differential equation. So what we are going to try is to solve the simplest form, which is Vs equal to 0, and that gives us Rc dVc by dt plus Vs equal to 0. Right? That is actually the Vs equal to 0. So any idea what this will lead to? What will be the solution for this? What is the solution for this LDE? Zero. The solution for this is Vc equal to 0. One of them is 0. What is the general solution then? Okay, so let us try to quickly solve this. So what this kind of equation, what is this called? What we looked at earlier is the first order LDE. When you said the independent Vs equal to 0, what is this kind of equation called? It's called a homogeneous equation. Okay, this is called a homogeneous equation, and if you had to solve this equation, of course the trivial solution is Vc equal to 0, but we are interested in the more general form of the solution. So we'll write it as dVc by dt equals minus 1 by Rc times Vc. Okay, and we need to solve this equation. What is the solution for Vc? So you are taking the derivative of Vc and you are getting so you are taking the derivative of some function. Vc is some function of t. Okay, you are taking its derivative and you are getting the same function but scaled in some form. You have already seen you already know, I think, what kind of function leads to this. It's an exponential function, right? So the solution for Vc needs to be some kind of exponential and not just 0, right? 0 is a very trivial solution, but it is some kind of exponential. Okay, what kind of exponential is it? If you had to write down the general expression for Vc, any idea what this would lead to? What is it? V naught e power minus t by Rc. I think all of you may already have seen this RC circuit and its solution, is it? Okay, fine. I'll call this Vc naught. Now, of course, you know that 0 is a specific solution, right? So why is this solution an exponential? So you take this, right? What this is telling you is the voltage across the capacitor is going to be some kind of exponential, right? But you have a resistor, you have a capacitor, you have no voltage source, you have no current source. So why do you get an exponential? Because initially the capacitor could be charged. Okay, if you have an initial charge on the capacitor, okay, then you will get an exponential. If you have no charge, which is a special case, which is a trivial case, of course Vc will be 0. So Vc naught is the initial voltage on the capacitor. So suppose I try to plot as a function of time, I try to plot Vc, okay. Let us say some Vc naught was some 5 volts. What is going to happen? You start off with some initial charge, okay. Now the capacitor is going to discharge through the resistor, okay. What will be the current that will flow? What will be the current that will be the instantaneous current that will be discharging the capacitor? Vc naught by R, right? The minute if you look at the direction of flow of current, if you assume that the voltage is positive in this way, okay, the current will flow in this direction, of course. Okay, so keep track of the signs. I am not keeping track of the signs here because I think it's more or less obvious, but make sure in these circuits that you keep track of the signs of Vc, Vr, Ic, Ir. Okay, you have to be very careful with these. In this particular case, if you assume Vc naught is positive, then the current is in this direction. So the capacitor voltage will of course decrease. Then what happens? It decreases for a very short instant of time. It will look linear. Then what happens? Of course, it won't stay linear because now the voltage across the capacitor is reducing. Okay, the minute is reducing, the current will also reduce. Okay, so which is why we get our solution, which is an exponential solution. Okay, and this is Vc naught. This is your exponential solution. Okay, and this is of course asymptotic to the x-axis, right? It will take infinite time for the charge across the capacitor to go to 0. Okay. So similarly, let me use an axis here. If you wanted to plot IC, what will that look like? What will IC look like? Same. Just divided by R. It will be negative. That's why I specifically told you just 2 minutes ago, keep track of the signs. Okay. Look at the direction we have taken for IC. Okay. We have assumed that IC is flowing downwards, but of course you know that when Vs is 0, the capacitor is discharging, the current will flow in the opposite direction. Okay. So the instantaneous current through the capacitor is going to be, I'll call that IC naught, but it is actually 5 volts by R. Okay, that is going to be the instantaneous current. But what will be the profile of this current versus time? It will also be an exponential, right? The current through the capacitor is C dVc by dt. The voltage is an exponential, current is an exponential. That is exactly what we solved. Okay, the current will look something like this. It is a negative exponential asymptotically going to the x-axis. You wait for a long enough time, the current through the capacitor is also 0. Okay, now if you can again, the minute you know the voltage across the capacitor and current through the capacitor, you can of course find VR and IR also. You can do both of these also. Now let us say we are actually going to go ahead and solve the more general case. Okay, we are going to solve the more general case. I'll write it in the same form. Okay, this is the more general case that we want to solve. Actually, before we go there, I just wanted to point out something. We have these two exponentials. Let us look at Vc. I want to find out what the initial slope of this exponential is. What is the initial slope? So if I want to find out the initial slope, what is the initial slope of Vc? So dVc by dt at t equal to 0. This is what I am trying to calculate. Okay, and you can see clearly that this is also IC of 0 by C. Okay, what is this? IR of 0 by C. What is IR of 0? VR of 0 by RC. That is the same as Vc of 0 by RC. Okay, so, and of course you have a negative sign here. Okay, because IC is with the directions taken, okay, sorry, this one need not have a negative sign, but it will be minus Vc of 0 by Rc with the directions taken as we did. Okay. Now this Rc itself, you have seen that, you have seen this before. It has a very specific name. What is that? It is called the time constant. So first of all, this if you go back to your equation, let us say this equation, you can clearly see that Rc needs to have dimensions of time, okay, and this Rc is called the time constant of the circuit. I'll just call it the time constant. Sometimes you will see people using tau, right? The symbol tau to represent the time constant. Now, yeah, before we go on to the more general case, so what does this time constant represent? Of course, in a very general case, it represents the time taken for the initial charge across the capacitor to discharge completely, right? It will give you an idea of how long the capacitor takes to discharge, right? Even though the capacitor discharges, asymptotically, it will tell you how long it's going to take. If you are, for example, if your resistor and capacitor values are very large, right? Then you will get a curve which will look like this. It will look like this. You will get a very slowly decaying exponential. Similarly, you get something like this. If you have a very, very small value of, if you have very, if you have very small values of R and C, okay, what will happen is the RC time constant will be very small, okay, and you will see that the circuit will also discharge very fast. Now, of course, this RC time constant, of course, it has two terms. One is the resistor, other is the capacitor. Okay, if the resistor is very large, okay, what you are saying is the current, right? So suppose the capacitor has some initial charge, right? The current that is discharging the capacitor will be very, very small, right? And it takes a really long time to discharge the capacitor. On the other hand, suppose your capacitor was very large, okay, your resistance could still be small, but the discharge rate, the capacitor is so large, it is able to hold a lot of charge, so the time it takes to discharge so much charge is really, really long. There are two ways to look at this, okay, the specific case could be either of these. Okay, now let us come to the more general solution, okay, so this is your RC dVc by dt plus Vc equal to Vs. Now I'll write it in a slightly different form, dVc by dt plus Vc by Rc equals Vs by Rc. Okay. Now, how do you solve this? You must have seen cases like this before in the maths course. How do you solve this? Yes, anybody? How do you solve this? You must have solved equations like this, right? You wouldn't have solved only the homogeneous equations. You must have solved more general cases like this, because the homogeneous equation is a very, very specific case. It is not useful except in that case, right? How do you solve this? Okay, even if you don't know it before, how would you solve this? You learnt differential equations just last semester, right? Or when? Huh? Only for JEE. Okay. Okay, then let's then think back to JEE and tell me how to solve this. Or at least come up with some ideas as to how to proceed. What is this? multiply both sides by e power t by RC. Okay, then what? Okay, then integrate the other side. Okay, something simpler. What is that? Okay, right. So you can actually see what you know how to solve already is the homogeneous equation. Okay, if you find some way to make this look like a homogeneous equation, okay, then you can solve it very easily. Right? How do you make this look like a homogeneous equation? Replace the variable Vc with another variable such that you get a 0 on the right hand side. What is the most obvious thing to do? So you take this guy, bring it here, you will get a minus Vs by Rc. Okay, so right, if you write it in this manner, then what do? I'll define a new variable Vc1, okay, which is Vc minus Vs. This is what you meant, right? So Vc1 of t is Vc of t minus Vs. What is dVc1 by dt? This is the same as dVc by dt. Yes, it can. But we will, okay, good point. So maybe let us go back to our original case. So as he pointed out, Vs can change with respect to time, but very specifically, okay, we are not used to working with Vs changing with time, right? So maybe we'll start off with constant. Okay, sorry, maybe I should have mentioned that. That would have obviously brought out the solution immediately. So if Vs of t is a constant voltage, okay, Vs, this is called, we have not used this terminology in this course before, okay, but this is called it's called a DC voltage. Okay, whenever the voltage is constant, it's called a DC voltage. DC stands for direct current. Okay, it is also common to say DC current, even though it may sound silly. Okay, it is very common. Okay, the other kind of voltage that is also common is what is called AC, alternating current. Okay, which is where it does vary with respect to time in a specific manner. We will encounter AC also later on in this course. Okay, so for now we will learn how to deal with DC. It is easier to solve this differential equation for DC. The minute you have AC, obviously it becomes more complicated. Okay, we will deal with that a little bit later once we have the tools to deal with AC also. So you have DC voltage and DC current. So we'll assume that Vs is constant. Okay, and we'll say Vc1 is Vc minus Vs, dVc1 by dt is dVc by dt. Okay, and now we can rewrite this equation in the homogeneous form for Vc1. Okay, is exponential is Vc10 exponential minus t by Rc. Okay, this is your homogeneous equation. This is a solution to, okay, okay, this was the homogeneous equation for Vc1, and this will be the solution. Now you can go in and find out what Vc1 is put in what is Vc1 in terms of Vc, put in what is Vc10 in terms of Vc0. Okay, what is Vc0? What is Vc10 in terms of Vc0? Sorry. What is Vc10 in terms of Vc0? Is Vc0 minus Vs, right? Vc1 is Vc minus Vs. Okay, I'll make this more specific by putting it in terms of time. So Vc of t is Vs plus of course Vc10, so I'll call that Vc0 minus Vs exponential minus t by Rc. Okay? And let us see if this works out for the special case where Vs was set to 0. Is this okay so far? Okay. Let us see what happens when you set Vs equal to 0. What you get is so this is exactly what we got in the earlier case, so that looks good. Okay, so that looks good so far. Then what else can we do to check whether the solution looks okay? Suppose Vc of 0 was 0. What happens? I think you might have already encountered that case. Suppose Vc naught was 0. Remember, Vc subscript 0 is the same as Vc at time equal to 0. I am just using the subscript to make it easier. Okay, so suppose you had this case, then Vc of t is Vs minus Vs exponential minus t by Rc. This is also a very specific case. The solution for the case when the initial charge across the capacitor is 0. Okay, and you are applying an external DC voltage. So I'll slightly simplify it, rewrite it as Vs into 1 minus exponential minus t by Rc, which is the most standard form. So now again for this case you can plot what Vc of t will look like. What does this look like? The initial voltage when t equal to 0, the voltage is 0. It should be that way because Vc of 0 is 0. Okay, and what is the final voltage when t equal to infinity? Voltage is Vs. The capacitor is fully charged. This is Vs. So the voltage across the capacitor will look like what is in the blue in the black curve. What is the initial slope of this curve? The slope at t equal to 0. How do you find out the slope? What is it? Vs by Rc. Okay. The initial slope so that's why this Rc time constant is very important in many different ways. It tells you what the initial slope, initial rate of increase of the voltage, okay, in both cases. Any questions? Of course, if you had this voltage Vs could also be negative. I have shown it here as being positive, but it could also be negative. Now, before we go further, I just had one quick question for you people. When we try to solve this particular circuit, we got a first order linear differential equation, right? Now when will you get a higher order differential equation? Why did we get only a first order? Any idea why we only got a first order differential equation? We have one capacitor in the circuit. Okay, the relationship between its voltage and current is a derivative function. Okay, so we got a first order differential equation. If you had more than one capacitor in the circuit, okay, you could potentially get a higher order differential equation. Okay, if you had, but not in this very simple circuit. Okay, this particular simple circuit you may not get it, but if I actually gave you a circuit like this, okay, and let's say I am interested in this R1, C1, and I am interested in the voltage here, okay, you could potentially get a higher order differential equation. Okay, when you try to, you set up the KVL, KCL elemental relationships, you could get a higher order differential equation, and obviously it gets tougher and tougher to solve this. Okay, and we will look at special cases of this in a few classes, right? But as it turns out, beyond a certain point, it's going to be very difficult to handle this, higher order differential equations. We will also learn techniques to solve them in a much easier manner also. Okay, so let us come back to this particular general circuit. So this particular circuit has this particular expression. Okay, has two portions. Let us. I'll pull this out. This is the general solution for the differential equation. So Vc of t is Vs plus Vc of 0 minus Vs exponential minus t by Rc. Now you can see this has two terms here. One particular term is a function only of Vs, okay, of the DC voltage that is applied to the circuit. The second particular term is a function of the initial voltage across the capacitor, Vs, as well as and Vs, right? That's number one. Number two, the first term is not a function of time. The second portion is a function of time, right? So you can actually, there are many names for these two terms, right? So let us look at what they are. So the first term is also called the steady state response, because as you can clearly see, if you wait for the system to reach a steady state, in other words, you wait for a long enough period of time, the second term will go to 0 and the voltage will just be the voltage, applied voltage, which is Vs. So you can think of it as a sum of the steady state response and the transient response. Another term that is used to describe these, because Vs happens to be the external applied voltage, okay, the first term is often called the forced response, okay. And the second term, which actually depends on the initial condition of the capacitor and just the time constant of the circuit, okay, is often called the natural response. So similarly, you can think of it as any other terms anybody knows for this? If you had set Vs to 0, what would the second term have become? Vc of 0 exponential minus t by RC. What is that? That is the homogeneous, the solution to the homogeneous equation, right? So you can think of it as a particular solution plus solution to the homogeneous equation. Similarly, you could also have split the two functions in a slightly different manner. If I had written it as Vs into 1 minus exponential minus t by Rc, okay, plus Vc of 0 exponential minus t by Rc. Okay, this is also called the first term is often called the zero state response. Okay, so this is the response when Vc of 0 is 0, right? The initial state of the capacitor is 0. And the second term, what is that? That is a solution when Vs equal to 0. So that is also called the zero input response. Okay. Anyways, let's stop here and we'll continue with more on RC circuits tomorrow. On Friday, because Thursday happens to be a tutorial class, so we'll continue it on Friday.